So, welcome to lecture 33. This is going to be on a multi-transistor circuit using inspection analysis. So I'll give you an example of how to do this. As usual though, some announcements first. You have no homework due this coming Friday. That's kind of nice, but you do have a lab due this coming Friday. And I guess before even talking about that, today and tomorrow you have your second checkpoint due in the lab. And so this is where you should be showing your breadboard on Zoom to your GSI, show that you can put an input in and it gets some kind of output. I guess just show that it could be powered up, I suppose. And so this is meant to ensure that you have not procrastinated till the end, that at least you've started hooking up your board, but hopefully by this time, since your lab is due this coming Friday, you have much more done than just a functional breadboard circuit that you have to demonstrate today. If you don't, then you're behind, and probably what you want ideally, and so moving down here, you probably should be focused on writing your report on Wednesday, I would say, to be in good shape for this, because remember, your report is what actually gets graded, so you want to make sure that you put enough time into that report, so hopefully by Wednesday you don't have to make any further measurements. Now, I will say that's hopefully. In past courses, there are of course people still making measurements even on Wednesday, maybe even on Thursday, but you probably don't want to be that person because that puts you without much time to write up your report. So really try to get all of that stuff done before Wednesday if you can. So that's lab number 5, and we're just sort of marching on. So lab number 6, that's going to post either today or tomorrow to give you an early look on that. That won't be due till the very last day of class, meaning the last day of the RRR week. So that's a ways off, but we at least want to give you a look at that. This is going to be a multi-transistor circuit, so similar to what we're talking about today and the next several lectures. You probably have noticed also that your lab grades are starting to come out, and they're almost all out. I guess lab 3 has to be finished, and already lab 4 pre-lab is done. So soon after, when those grades are done, I'm going to start sending you your z-scores, so you have a better idea of where you stand in the class. Other than that, are there any questions about logistics in the class? So you have no homework this week, but you will get a new homework this coming Friday that will not be due during Thanksgiving. That will actually be a 2-week homework. Okay, so nothing to worry about with that when you get that homework. All right, so let's talk lecture now. Let's move into the lecture. And so we're going to be doing a multi-transistor inspection analysis example, having completed all of this here, looking at the generally loaded transistor, looking at expressions for terminal resistances and terminal-to-terminal gains, and then looking at that inspection analysis sheet, which is something that you probably want to memorize, at least some of those equations, because that will allow you to do an analysis very quickly in the future. And I'm going to show you how to go about doing that analysis, and so I'm going to do it right here with this example. So this is a multi-transistor amplifier example. It's basically 2 transistors, 2 stages here. We've got common emitter with degeneration. So you can see that resistor there that survives after we short the bypass capacitor. That means that this, in a small signal sense, is a common emitter amplifier with emitter degeneration, meaning we have a resistor hanging off of the emitter node to ground. And then the second stage is a common collector. Since this is going to go up to VCC, that will be ground. So the collector is common here, and the output we're taking out of the emitter in this case. And so this is a typical amplifier, and we'll see that this is something that you might want to do if you're going to make an amplifier, because if you think of voltage to voltage amplifiers, usually what that means for a good voltage amplifier, we talked about this before, you want a high input resistance, you want a low output resistance, you want a lot of gain. And so this circuit will give you elements of all of those things. And so this is the circuit. I guess the classic thing that you'll be asked to do when you get a circuit like this is sort of find input resistance, find output resistance. Let me write that down here. So what you want to do is find input resistance find output resistance, find the gain, so V out over Vs in this case, and you want to find the cutoff frequency. So I'll say Fh. You could also find the low frequency cutoff, Fl, but we won't do that this time because you know how to do that, I suppose. Or you will in a homework there. And so we want all of these, and this is all a small signal analysis. But before we can do any small signal analysis, we have to be able to get the DC operating point of this, because this is what determines how this thing behaves in terms of all of these different parameters in the first place. So let's first find the DC operating point. So I'm going to do that in red. I don't know why that's doing all this stuff, but okay. Okay. Okay, so we first want to find this DC operating point. And how do we go about doing that? Well, you pretty much know how to do that. Let me move on to this side here. Give myself space. And so what you want to do is get all the DC voltages at each of these nodes. And especially you want to get the currents going through these transistors. So arguably the main thing you want to get is the current going through these transistors when we're doing small signal analysis. But as you're learning from your lab, you need to know these DC points as well, because that determines your swing out here. It'll determine how big this capacitor is right there. All sorts of things it determines. And so let's go ahead and do this. Usually when you do this, you want to start all the way on the left side here, because this is where your bias string is here, this R1 and R2. And so remember, putting VCC across R1 and R2, that's going to create a voltage right here. And so that's the first thing you want to do. You want to get this voltage, which is the base voltage of transistor 1. I'll call that VB1. And that, once you get that voltage, then that should yield very quickly this voltage right here, which is VE1, the voltage at the emitter of that Q1 transistor. And then you're going to have that voltage then across these resistors, and a voltage across the resistor creates a current that then gives you the current going through this circuit. So in the end, it's the voltage across the REs here, down here, that gives me the current. And in the end, that's going to give me what I want out of this, which is basically IC1. I want that DC bias current going through that. So let's go ahead and do this. So first of all, keep in mind that, I'm giving you this problem here, but if you were designing this thing, then a good design, somewhat red, for a good stable design, you want to make sure that what we called I bias is greater than the base current. So to be greater than that, you want it to be 10 times, much greater than that, you want it to be 10 times the base current. So this is the base current then going into Q1. And this current sort of right here is that I bias current. Sort of the current flowing through those resistors. This is basically saying that the current for the stage before the stage that's being biased up, that should be a much larger current than the base current going into the next stage. Okay? And so that's just a design point. If you want a good design, this is what you want to do. And hopefully you're doing this for your current lab. You're going to need to do this for lab 6 too, which is going to be a multi-transistor type lab. And so now let's go ahead and do the analysis here. And so I can write one equation and get that voltage VB1 as just the voltage division through R1 and R2. This should be R2. So I have R2 divided by R1 plus R2 times VCC. And so that's something that I'm writing, and as I write that, I'm basically neglecting base current. Right? So when I write this thing, this is basically saying that I'm neglecting IB1 relative to I bias, because I suppose I have a good design where I bias is much greater than IB1. Okay, and so if I can write this, and generally I can, then what that gives me is it gives me that base voltage, VB1, and so right away I can get the emitter voltage, VE1, under that. So VE1 then becomes equal to that base voltage minus the voltage drop from the base to the emitter of the transistor. And if I assume the transistor is in forward active, and we had a variable for that, we called that VBE on, that is a constant for us at 0.7 volts. Now in actuality it may not be exactly 0.7 volts, but it's going to be close to that, and so very close to that, so we're just going to say it's 0.7 volts. Alright, so you can see I've already made some approximations in doing this DC bias point here, and I'm making them because I'm assuming it's properly designed, so this I bias current is a lot larger than IB1, so I can neglect IB1. And then I'm also assuming that the on voltage of this Q1, the voltage drop across this VBE on, which I guess I can draw in here, I can just say is 0.7 volts for a forward active transistor. All right, so I've got that voltage drop, which means now I can get this current. So the current flowing through this, I really want IC1 up here. And let me write IC1 a bit nicer than I did there. So I want that IC1. And so that IC1 I can get pretty much by just getting the IE1. Because if I assume that beta is large, then alpha is going to be pretty much 1. And so IE1 is basically going to be equal to IC1. And I know my expression for IE1. That's going to be whatever the emitter voltage is divided by the resistance that we put it across. And so that's going to be RE1 plus what I'm calling RE1 prime here. Right? RE1 prime is sort of in parallel with this bypass capacitor. So once we go to small signal, RE1 prime will disappear and RE1 will remain. But for right now in DC, both of these resistors we have to care about. And so in the end, this current is going to be VB1 minus VBE on divided by RE1 plus RE1 prime. Okay, so that's now my collector current. And once I have my collector current, I can now get my collector voltage. Right, and so this voltage right here is going to be VC1. And so I can write out VC1 as just being equal to VCC minus the drop across resistor RC, which is just going to be IC1 times RC. And that then is also going to be equal to the voltage at the base of Q2. So I can call this node here is not only VC1, but it's also VB2. Okay, so now I have that base voltage, and if I have that base voltage, then right away, assuming that that last transistor Q2 is in the forward active region, I can write out that VE2 is just going to be equal to VBE or VB2. So VE2 is just going to be equal to VB2 minus VBE on again, and that again is a 0.7 volts. We're just going to assume when we're actually plugging in numbers. I won't plug in numbers for this problem here because that would just take a bit too much time. But I will at least write all of the equations there. So I have VE2, and once I have VE2 right here, this voltage, if I have that voltage, now I have the voltage drop across RE2, which means now I have the collector current IC2 running through Q2. And so to finish this problem off, I guess I'll still do it on the left side so I can keep the circuit there. I can then write that IC2 equals IE2, the emitter current, assuming alpha is pretty much 1, which is then going to be VE2 over RE2. Okay? And so there it is. I've done the DC analysis for this. I've got all the voltages and very specifically I want all the currents, but in the process I've got all the voltages as well. So just some remarks on the procedure that I just went through. When you're doing this DC analysis, remember current is generated by a voltage across a resistance. That's going to be universal. When you get to 140 and you have to look at a much more difficult circuit with a lot more transistors, and you want to know how that's biased up, what you look for is a resistor. Or you look for something that has a definite resistance and a definite voltage across it. And once you find that, that's what's generating your currents. So in this case, you're looking for resistors, but basically you're looking for well-defined voltages. And in this case, that's what VBE on is. So part of the remark here is you have to look for VBE ons, right? Because these are well-defined voltages. And then you want to know how that VBE on, maybe added or subtracted from some other voltage, is dropping across a resistor. And then that determines your current there. So I could say right away, from both these transistor cases here, you can see that the currents are really coming from a voltage drop across RE, and that's usually what you're going to see. So I'm going to write that currents are usually determined by an emitter voltage divided by an emitter resistor value. So I'm going to say it's usually determined by VE over REs. Okay, and then finally I'll repeat what I've already written there, but especially when you're doing design. If you want bias stability, what you're looking for is I bias for the first stage. I'll call that I bias 1. Let me call that I bias 1 there. You want that to be greater than 10 times IB1. You want that current to be greater than the base current. But also, for the second stage, you want I bias 2 to be much greater than its base current. But what is I bias 2? Well, if you look at this stage here, this is the base current coming into Q2. That's IB2. And so the current that's going down this branch here is really I bias. So that tells you that I bias here, my I bias 2 at least, that's just equal to IC1. Okay, so I can write I bias 2, which is equal to IC1. That you want to be greater than or equal to 10 times IB2. And that then helps ensure that you have a stable bias point. Okay, so you see how that's happening. I've got 2 transistors for each of these. To get a stable bias point, I basically want this current to be much larger than that base current, and I want this current to be much larger than that base current. The current that's feeding your circuit should be much larger than the base current of the next circuit. And in your lab number 6, you actually may have 4 transistors in series here, in a cascade like this. And so each time you go from one transistor to the next, make sure that that collector current for the previous transistor is 10 times higher than the base current for the next. And if you do that, then you're going to have a nice stable bias point. If you don't, you may run into some issues. You may not. But at least for the design, we're looking for a good design for lab number 6. We want to see that in your lab number 6 design. And of course, you're already getting experience doing that in your lab number 5. Okay? So, that's the DC bias point. Anytime you're trying to design an amplifier or analyze it, you're going to have to get that DC bias point. So hopefully you've seen all the shortcuts and approximations that I make to make this a much easier problem. You could do this by plugging in the transistor equations for VBE and get some very accurate numbers where VBE is not just 0.7 volts, it's 0.70754 or something, but that's a complete waste of your time if you try to do that. Try to do it the way that I just did it here. All right, so we've got the bias point. Next, we want to get those small signal values that we talked about. And so I want to do a mid-band small signal analysis. So as opposed to a high frequency or a low frequency analysis. And so let me title this. We're now moving into doing our mid-band small signal analysis. And we're going to do this specifically to get our gain, to get our input resistance, and to get our output resistance. All right? And so to do this small signal analysis, we talked about the procedure for doing small signal analysis, and nothing changes from that procedure. Okay, we did it before for smaller circuits, single transistor common emitter circuit. It's no different for this. So the first thing we want to do is draw out our small signal circuit. And so to draw out the small signal circuit, you have to zero out VCC. And you want to short all the big capacitors here. And so if I go ahead and do that, this is what the circuit becomes. So there's my source. I'm going to have a source resistance, RS, right there. I'm going to have that R1 and R2, where in the past what I've done was just call that RBB, so I'm just going to do that again as a shorthand. R1 in parallel with R2. Let me pull this over and let me give myself a little more space here too. As I do this, I'm going to pull this down a bit. Okay, then I have my transistor Q1. You can see that this capacitor CE1, it shorts out, so I get rid of this RE1 prime, but I'm left with RE1. So I still have RE1 there, and then I've also, with this transistor, have a collector resistor, RC1, that's going to ground there. And beyond this, I then can come out to my, let me do one thing in preparation for what's about to happen later on. And I'm going to make this just a little longer here. I'm doing this because I'm going to do a high frequency analysis later on. So I want enough space to be able to draw in capacitors after this. No, that won't grab the whole thing. So okay, and so this I'm going to take all the way out to Q2. So that's Q1. That's Q2. Q2 also loaded with emitter resistor RE2. And then this final bypass capacitor, or coupling capacitor at the output gets shorted. So at my output, I directly see RL, and there's my output voltage V0. Okay, so this is my small signal circuit that I now would like to analyze. And I guess what I'm going to do is I'm going to grab this and store it away somewhere here. Let me just grab this, store it away somewhere. Let me put it down here. Because when I get to high frequency analysis, I'm going to want to use that again. But for right now, we're going to do our mid-band analysis here. So we're not going to put any capacitors in here. We're just going to analyze this as is here. So we want to get, again, small signal input resistance, small signal output resistance, gain, and frequency. And I guess on this side, the way that I wrote input resistance is bugging me just a little bit because it doesn't look like it's input resistance, so I'm going to rewrite it. There we go. All right, so on the left side, let's go ahead and start this problem here. I want this input resistance. And I guess the input resistance, because the amplifier is really everything after RS and everything before RL. So my actual input resistance is going to be right here. Maybe I should have left a little more space in there, but I can squeeze that in there. And so how do I go about getting this input resistance? Well, I can draw in hybrid pi models for each of the transistors, but why am I doing that? Because when I look in this direction, I see this RBB in parallel with whatever's looking in this way into the transistor. But whatever's looking this way into the transistor, if I look that, I can just get by inspection analysis. And so I'm going to do this now, but in the future, do not do this. Don't go back and forth between these inspection formulas, but we're really looking at this resistance R little b. We plugged in the hybrid pi model, and we derived what that is. If I have an R little b looking this way, this is the expression for R little b, either this one or this one. I'm going to write out this one, so it's going to be R pi plus beta plus 1 times whatever that resistor is right there. Let me take this out of the way here. So right away, this resistance, I'm just going to write as R pi of transistor 1 plus beta plus 1. And I can put beta sub 1 if I want for transistor 1, and then there's beta sub 2 for transistor 2. But I'm going to assume the transistors have the same beta here. But this is beta plus 1 then times the emitter resistor RE1. And that's the resistance I see looking this way. So the total, this way. So the total resistance I see there is the parallel combination of RBB and this resistance here. So right away, I can just by inspection write out Ri as just being equal to RBB in parallel with R pi 1 plus beta plus 1 times RE1. And that's it. Right away, by just inspection, I have written that input resistance without drawing any hybrid pi models for this whole thing. I could do a similar thing for my output resistance here. So there's my output resistance R0. And so for my output resistance, what do I see? I'm going to see, let me start writing it here. So R0 is going to be equal to, well, I'm going to have some resistance seen looking down that direction. I'm going to see some resistance looking up in this direction. And so looking down in that direction, obviously I just have the resistor RE2 that's going to ground. Okay? And when I'm getting these resistors, remember what we did. We're getting the resistance from that node to ground is what we're getting. So this was the resistance from this node to ground. What I'm getting now is the resistance from this node to ground. RE2 is going to ground. That's one of them. But it's going to be in parallel with the resistance I see looking up in this direction to ground. And so one resistance that I see looking in this direction is R0 of 2. Right, so I see that R0 of 2, and so I could just say that's going to be in parallel with R0 of 2, but then I'm going to be looking at something in parallel with the resistance seen going into the emitter and looking that way. And so you can go back from your from what we've looked at before to get this whole expression here. This is going to be whatever resistance I see looking up this way. Well, no, let me not do that. Let me use this inspection analysis formula so you can see what we're doing. Now we're looking at resistance looking up into the emitter. So it's this equation here. So if I'm looking up into the emitter, what do I have to do? I have to add R pi. I include R pi. Then I add to that all the resistance seen looking out of the base. Out in this direction. It's not the shunt resistance, but it's resistance looking in this direction to the left. Okay, and then I divide that by beta plus 1. That's what that resistance is going to be. And so I'm basically going to take R pi, okay, which is going to be part of that resistance, but then I want to add to it all this resistance that I see looking in this direction here. And so this is going to be a pretty big resistance, so let me just start writing it out here. So I'm going to write out R pi 2, but then I have to add to that the resistance I see looking in this direction. And in this direction, what do I see? I see RC1 in parallel with all the resistance, and RC1 is that resistance looking up that way. Then I have all this resistance looking down that way. And remember, that had a pretty gnarly equation associated with it. So here's that equation. RC, looking down in this direction, that's R0 of this transistor times 1 plus, it's GM times this RE resistance, divided by 1 plus RB over R pi. Okay? And so if I look at that equation, and I try to reproduce that here, this is going to be that RC1 in parallel with R01. Okay, and then that R01 is going to have to be multiplied by all that stuff. So I'm going to have a 1 plus a GM1 times RE of 4 divided by 1 plus whatever the resistance is looking this direction now from Q1. So if I look in that direction, what do I get? I get RS parallel with RBB. And so that's what I'm going to write here. RS parallel with RBB. And then that's going to be divided. So again, go back to this equation. That's now divided by R pi. So I'm going to take that and divide it by R pi of transistor 1. And that then becomes that resistance that I see looking down in this direction. Okay, so if I wanted to be absolutely complete, I'm looking at R down here, R pi 2 plus all of this stuff up here. RC1 parallel with R01 times 1 plus, I should say GM1 up here, times RE4 divided by 1 plus RS plus RBB divided by R pi 1. That whole thing there. But I'm not done yet because I'm still in the midst of getting the resistance seen looking up this way. All I did was take R pi of Q2, added all of this resistance here to that, and then I've got to divide that now by the beta of Q2. So I will write that as beta of 2. And that then becomes one of those terms that I'm putting in parallel with these two right here. So it can get really complicated. It can look really complicated. And as you're looking at this, you may be thinking, gee, inspection analysis is not that easy. But just think of what your, that should be RE2, sorry. No, it should be RE1. Someone put in the chat, what is RE4? You're right. There is no RE4. It's RE1. I don't know why I put 4 there instead of 1. Let's see. Anything else? Okay. And so, yeah, but if you had to use the hybrid pi, this would be horrible to try to rederive all this stuff here. What is all divided by beta plus 1? So all of this stuff is divided by beta plus 1. That's coming from this equation right here. This is the equation looking up into RE. We're looking that way. So I have R pi. There's the R pi. It's R pi 2. And then it's all of this resistance, RB, looking out of the base. And so if I go back to the circuit here, all of this resistance looking out of the base is all of this stuff, which I copied right there. And then all of that stuff is divided by beta plus 1. Okay, and that would be the beta of transistor 2. Now in this problem, I'm assuming both transistors have the same beta, but that's where all of that comes from. So hopefully that's clear. I'm just going straight off of those inspection analysis equations there. Okay? Okay, good. But, you know, one thing I'll observe is that was all of this necessary? And so this is where, you know, this looks pretty hairy, but you need to be able to make some assumptions and some approximations. And so for one thing, you've got several resistors in parallel. You need to think about which is a big resistor, which is a small resistor. And so right away, if I look at this expression here, this is a big resistor, R02. Okay, so R02 is big, so I'm going to neglect it. Okay, this resistor here, R01, that forced us to times all this stuff, right? We had to memorize all this stuff. Well, there's no need to memorize all this stuff because, think about it, this whole thing, that's enormous. So I really don't need to care about that either. And so when I actually am doing this problem, the way that I did it for you is I included all these resistors so that you're not asking questions, well, what did he do with that resistor? Isn't there a resistor there? Isn't there a resistor there? But when I do this problem, I would never write this. I would not even write R02. I would just go straight in and I would write, I guess in this case I do have to go on this side here. I would go straight in and just write that R0. All right, let me at least keep that red. is going to be equal to RE2 in parallel with the other small component, R pi 2 plus RC1 divided by beta plus 1. Okay, that now becomes my expression for R naught. And that's going to be part of my answer. So part of my answer already is this Ri. That's an answer. And then finally, the other answer I'm going to give for the output resistance is just this. And you notice that in this case, I brought in these inspection formulas. And you should have all these memorized, but I didn't even have to use this one. Okay, this is it's a horrid one to memorize, and if you don't remember it, most often this is going to be in parallel with something else much smaller. In this case, that was RC1. And so all that complexity just disappeared, and I don't even write it down. On an exam, I don't even write it down. I just say resistance looking down that way is big, and I just write RC1. Okay, unless the exam says to explicitly write it down. But if the exam just says get me or not, I wouldn't even write that big thing. I would just put RC1 down. So you could see, you could do this a lot faster than I just did it by just ignoring these big things. And that's going to be the big secret to inspection analysis. What can you ignore, what can you not ignore? Okay, and so now let's keep going with this. Let's get the gain. Let me do that in green now. And of course the gain is V naught over Vs. So that's what I want. I want the gain, and now I do want to go back here and get back to the circuit so you can see, to the small signal circuit. There it is. And so remember, to get gain, I'm doing node to node analysis. That was weird. Let me check something here. Okay, that is okay. So I'm doing node to node analysis to get the gain. So I want to identify some nodes on this whole thing. So I'm going to go ahead and do that. Let me call this node 1. Whoops. Let me stay green here for gain. So that's my node 1. There's my node 2. This is my node 3. And finally, I'll call this node 4. So obviously node 1 and 4 are the same as Vs and V naught, which I'll replace them with later on. But I just want to do this just to show that I'm doing this node to node now. And so to get this gain, and so this is gain from node 1 to node 4. Okay? And so to get that gain, I've got to get the gain in stages here. Right? I can write out that V out over Vs, that's going to be equal to the gain from node 1 to node 2. From node 2 to node 3, and then times the gain from node 4 or 3 to node 4. Right? So I'm basically going to get each of those gains, and I'm going to multiply them together. But while I get these gains, I'm going to take into account loading from the next stage. And that's where I need to know those expressions, those inspection equations for resistance to ground at a certain node in a certain direction. Okay, so let's start this out. I need this first gain here, V2 over V1. And if I break it down and I'm going one at a time, it becomes much easier. And so this, of course, is the same as my source voltage, Vs, to V2. And in this case, it's obvious what that is here. This is just going to be the voltage divider between Rs and this resistance Ri. So Ri is all of the resistance looking in this direction to ground, right? And so basically I can just write this as Ri over Rs plus Ri. And just, we know what Ri is, right? We already wrote that down, but just to be complete, I'll write this whole thing as RBB times R pi 1 plus beta plus 1 times RE1 divided by Rs plus that exact same thing. Okay? And so this voltage is just the voltage divider equation, which I hope you've already have memorized. Right, that one you should have memorized from previous courses there. I mean, I can look at this thing. It depends on what RS is and the rest of this, but probably this is going to be about equal to 1. So even this, I might not even write down. I would just say is 1, but I'm just trying to be complete for you right now. And so that's the gain from 1 to 2. Now I need the gain from 2 to 3. And so let's write this out. And we're going to do this by inspection because we have our inspection formula for this. This is just the gain from the base to the collector. And so in our inspection formula, I want base to collector gain. There it is. VC over VB, it's just a minus capital GM times all the resistance in shunt with node C in this case. And so going back to here, this is also going to be minus GM. I guess I'll say minus GM of device 1 times all that resistance in shunt with node C, with node C1 I'll call it because it's associated with the transistor 1. So all the resistance in shunt with this node right here that I'm pointing at. Okay, and so I know what GM is, capital GM, because from the inspection formula here, for at least base to collector gain, if I have an emitter resistor, that's going to be little gm over 1 plus little gm times Re. So I'm just going to write that in here. This is going to be minus quantity little gm1 divided by 1 plus little gm1 times Re1. That's my effective GM there, and now I need to multiply that by that resistance that I see out there. And that resistance I will write out completely for first time just to be complete. So it's going to be that RC1 in parallel with that big equation. That might be difficult to memorize, but maybe it won't be necessary in most cases. So this would be the complete formulation of that. Okay, so I've got RC1 up in this. So here, I got RC1 looking up that way. I've got that resistance looking down this way. Okay, but then, I'm not done. I want all the shunt resistance to this node. So I have more resistance looking in that direction. And the resistance looking in that direction, using my inspection formula again, is just this. R pi 2 plus beta plus 1 times Re2 in parallel with RL. Okay, and if I wanted to be very complete, I guess I could say it's parallel with R0 2. So in this whole thing, I'm not quite done. I shouldn't have put that bracket there. I've got this, and so I need to put something in there, and what goes in there is what I just wrote. So this whole thing goes into there, and then I can finish the brackets there. And that then becomes that total resistance, but I can identify this as being large. I can identify this as being large. So in the end, this gain V3 over V2, I'm just going to write as minus this GM1 times all of this resistance here, which I'm just going to say is RC1, divided by 1 plus GM1 times Re1. So the gain for that second stage becomes very simple when I take into account that these are very large resistors compared to RC1. And how do you know that they're large resistors? Well, you have to have that experience. So for one thing, we talked about R01. That's already 100 kilo ohms. RC1 is usually going to be in the kilo ohm range, single digit kilo ohm range. And so if I have 100 kilo ohms compared to 5 kilo ohms, the 5 kilo ohms wins. The 100 kilo ohms just goes away when they're put in parallel. Okay, so that's the gain from 2 to 3. Now I need the gain from 3 to 4. And so I guess I will do that in brown color here. And so just looking at this circuit from 3 to 4, this is now base to emitter gain. And from our inspection analysis formula, which we derived last time, right? I'm not just throwing formulas at you. We derived all of these things before. It's really just going to come down to whatever resistance I have hanging off of this node here, looking out in this direction here to ground, in a voltage divider with the little Re, which is a 1 over GM there. And so all I need is this resistance looking there to ground. And so in this thing, I sort of can see that. If I look out this way, I'm going to see RL, I'm going to see RA2. I also see this R02 there. So I can just write right away that the gain from 3 to 4 is just going to be equal to RE2 parallel RL, my load resistance, parallel R02, divided by that little RE2, which remember is just 1 over GM of 2, plus this same resistance, RE2 parallel RL parallel R02. Now, in general, this is much greater than RE2, right? RE2 is 1 over GM, and remember, 1 over GM, that's a small value. That's on the order of 25 ohms. So in this case, if these resistors are much bigger than that, then this gain is pretty much 1. And that's what this thing does. This is an emitter follower. It gives you a gain of about 1 in the end. And so with all of this, calculating all that there, and putting all of these gains together, there's my first gain up here, there's my second gain right here, there's my third gain right here, I can write out the whole gain for this problem, which I'm going to do right here, and just say therefore, so rewriting this, V0 over Vs, that's equal to all of these gains multiplied together, so V of 2 over V of 1 times V of 3 over V of 2 times V of 4 over V of 3. All of these gains put together then give me my total gain as minus RBB parallel with R pi 1 plus beta plus 1 times RE1. All I'm doing is copying results from this page back here, divided by RS plus RBB, and all this stuff, this whole thing times this second gain stage here, which is this GM thing here. So I'm going to write out GM1 times RC1 divided by 1 plus GM1 times RE of 1, and that then is my gain, which I got by inspection analysis. And if I think about this, depends on what RS is, right? I could say if RS is small, which often it is, then I can really just write out this. Just ignore that first voltage divider term, which basically goes to 1 if RS is very small. Okay? So if you're going to be very accurate about everything, your equations can be a bit intimidating, but often it's not needed to be this accurate, so this whole thing boils down to something that you could have done in less than 30 seconds if you just had the experience to know that that first stage gain is about 1, that last stage gain is about 1. All you had to do was look at the second stage and just write down this. And this is what I would have done with this problem. Provided RS was small, if it were me working on this problem for real, I would have just focused on the second stage. Okay, this is not moving for some reason. Okay, I would have just focused on this stage right here, ignored this, ignored that, and just pulled the gain right out there, and be done within 30 seconds, specifying that gain. So hopefully you can notice that that's what's happening with this. And so now, let me see if I really can squeeze this in. I don't think I can squeeze it the way I want to squeeze it. I'll squeeze it later on, but I want to put this in and I want to put this in, I guess. So let's just summarize this procedure for mid-band gain inspection analysis here. And so what did we do when we did all of this? We identified and labeled all the signal path nodes. And so the signal path in this obviously goes from here to there to there. It didn't go through here, right? This is not in the signal path, but these nodes are in the signal path. So that's why we specified 1, 2, 3, and 4 as those nodes. Get the stage gain from node to node. For each stage, count for loading by the next stage, specifically load resistance to ground. You notice how we did that in this case, even for this voltage divider. We had a voltage divider RS going into some load here, but this load that we're looking at included not only RBB, but also all the resistance seen looking that way. We did that for here too. When we wanted to get all the resistance at this node, we looked at that RC, but we also looked even at the resistance looking down this way back into Q1, and we looked at the resistance going in that direction. These other resistors turned out to be very small, but that's not always the case, right? If it wasn't the case, then I couldn't just write RC1. I'd have to write down RC1 in parallel with these other resistors. And so that's what we did for transistor terminal gains, right? You'll likely need to determine the output node resistance to ground, including loading by the next stage and even the influence of loading by the previous stage when determining RC. So you notice when I got that resistance looking down this way into Q1, I had to take into account this base resistance, this resistance hanging off the base. So even the previous stage impacted that resistance that I was looking at going in that direction. Okay, once I get all these stage to stage gains here from node to node, take the product of all the node to node gains to get the total gain. You could do all of this by inspection, which is what I did. One, if there's no feedback. So that's an important thing with this circuit. There's no feedback in this circuit. I don't have some branch coming back from here back to somewhere there. If there is feedback, you can't do what I just did, because feedback sticks a whole wrench in there. If there is feedback, what you have to do is go back to the hybrid pi model, plug them in, and do that analysis. And it's going to take time, but it's the only way to handle something that has feedback in it. There are other better ways to handle feedback. That I guess what I said is not true. You don't have to go to hybrid pi, but those things you don't learn until the end of ee140. Okay, when you really start tackling feedback problems. But for right now, for this class, you can do this inspection analysis if you see no feedback, if you know all the terminal gain equations, okay, or you can see or derive them quickly. So that's why I say memorize these things. There's not that many of them. You know all the equations for the resistance looking into the transistor terminals to ground, or you can see or derive them quickly. By see or derive, I mean you can do things like follow the currents, which is something I talked about in the last lecture. And then you can see or derive quickly can often be, I just said that, by following the currents. Okay, so that's the procedure for mid-band gain inspection analysis. We just finished that. And so what I want to do next, and I guess we'll do this in the next lecture, but what we're going to do next is the high-frequency inspection analysis. For that exact same circuit, we're going to do that. And so let me just talk about what that entails. That entails identifying and labeling all the signal path nodes. We just did that already, so we don't have to do that again. We did that for the stage gain. Draw in the small signal transistor capacitor. So in this small signal circuit, that's why I reserved this circuit right here. But I'll just go to this. In the small signal circuit that we have, what I'm going to want to do is draw in all my capacitors for this circuit there. And then if I don't want to memorize the driving point resistance for CME1, well, why don't I do this a little bit here? I'm going to do a little bit of while I talk about this. So I'm going to go to that circuit that I saved back here. So this is that circuit. And so I would do the same kind of thing that I did before. I'm just going to, I won't finish this. I'll just start this out just so that you can understand better from what was written there. See, that's 1, 2. That would be 3, and this would be 4. And then what I would do is I would draw in my small capacitors. And so that would be associated with Q1, a C pi 1, and a C mu 1. Okay, I know I have those capacitors, and I guess I'm even going to put in CCS1. Okay, same thing for Q2. I'll draw out these capacitors knowing that they're really contained inside the small signal model for these. And then here I'm going to have a CCS2 right here. I'll use this for next time too. But I draw in those capacitors. And then for C mu 1, I would have to memorize that equation for the driving point resistance. That equation is right here in your small signal formula thing. So that's this equation here. I have that memorized, but if you don't, you didn't need to memorize it because you can convert that to a Miller capacitance, use the Miller transform, and then you don't have to memorize anything. For base to emitter, so this type of capacitance, C pi 1, C pi 2, or gate to source if we're doing MOS, which we'll do later, you'll need to know the equation. This is feedback here. Right? There's nothing you can do about that in this case. This is feedback, that's feedback. You can't really do the Miller transformation well with this. It doesn't work well with this because the gain is not high and it's not negative. So you have to memorize that equation, but I'll show you tricks where you really don't later on. Then you get the time constant for each node. I get one for node 2, for node 3, for node 4, and then I have to take these capacitors that are in feedback by themselves. I'm going to have to know right here, handle each feedback capacitor separately using their driving point resistance equation, which I have memorized. Then you add up all the time constants and take the reciprocal, and that gives you omega h. Okay, this is what we'll do in the next lecture. But hopefully you're getting the hang of this. You're understanding better how you can attack larger transistor problems by just memorizing some of these equations, right? You don't even have to have all of them, but some of them. Just memorize some of them, and boom, you'll be able to do this analysis very quickly. I took the whole lecture to do this gain because I want to teach you how to do it. I want to show you all the different things, but honestly, the input resistances and output resistance and gain, I could have done in 1 minute. Okay, and I think you will be able to in a few lectures too, and with a few homework assignments and a few labs under your belt. But that's it for today. I will see you on Wednesday.